Welcome everyone to this new video. In this first video of Prosper, we are going to learn how to set up a vertical gas producer well. And we will answer 3 questions to our production team. The first question is going to be what is going to be the initial gas rate if the wellhead pressure is 500 psi. The second question is, please provide the well performance curve of the well. And the last question is going to be from our simulation, our numerical simulation thing is please export the VLP curve to a simulator like Eclipse or VIP. Okay, so let's start with the model. Okay. For modeling the well, we have this data. We have here the PVT data, the well data, the static geothermal gradient, and the reservoir data. As we can see, we have here many data: gas gravity, impurity, water salinity, the completion, thermal data, and so on. We will discuss this data when entering into the model. The first step for creating the Prosper model is double clicking here in the icon of Prosper. You double click here, you will get this screen. This screen is the screen of Prosper, the main screen of Prosper. In this screen, you have 6 different screens of 6 different, let's say, 6 different summary screens. Okay, here you have the version of the model, the license, and so on. Here you have this is called the option summary. In the option summary, you can select what kind of model you are going to create. Here, the fluid is going to be dry and wet gas. Okay, everything. The other parameters are going to be exactly as they are. The well is going to be produced by a tubing, using a tubing. The well is produced, is cased, and there are no artificial lift completions in this well. Okay, it's a natural flow well. So here, let's say done, and then we will get information to be entered in the other 4 screens. This one is the PVT data. In the PVT data, we are going to enter the PVT, the data that we have from the well. In this case, we don't have too much information. We have little information, and the information is like this. No, we have a gas gravity of 0.65. It's a very dry gas. Okay, with a separation pressure of 250, the condensate gas ratio is going to be 5, very low condensate, 5 barrels per million. The condensate gravity is 50. The water to gas ratio is 0. We're not going to produce water, and the salinity of the water is 1000. We have no impurities at all. So that's it. This is the PVT data that we have, so we cannot do anything else here. So click done. The next step is entering the data of the well, the completion, this one here. So here we have the screen of equipment data. In this screen we have 5 sections. The first one is the Deviation Survey. We can click here in the white button, and we will get this screen. Our well is a vertical well with total depth of 5,100 feet. So because it's vertical, the TVD and the MD, measured depth and true vertical depth, are exactly the same. So we can enter the survey as this. That's it. We don't need to enter anything else because the well is vertical. Okay, we can click done, and the survey is already entered into in our model. If we want to see a plot of our survey, we can click here in plot, and we will get this vertical well with no angle or cumulative displacement because the well is vertical. Okay, so that's it, and this is the total depth. The next step is the surface equipment, because we want to get the top nodes of our model, our wellhead. We are not going to model any surface equipment, so we are not going to click here. We are going to skip it. Okay. The next one is the downhole equipment. Here, we have to enter the downhole equipment. The downhole equipment here is very simple. We have one wellhead, one tubing, and one casing. So we have the wellhead, also called Christmas tree. Then we have the tubing and the production case. Here we can enter the label. The label is not really important, but you know, it's always fine to have it. Tubing and case. Okay, the measured depth is 0 for the wellhead because it's at surface. The tubing was set at 4800, and the casing was set at 5100. However, because of the datum of the reservoir is 5000. Okay, so in this screen, the biggest depth that you enter here, the biggest number is going to be the datum of the reservoir for the model. So although our casing here was set at 5100, we are going to stop the casing at 5000. Why? Because we want to say to the software, my datum is at 5000 and not at 5100. This difference of 100 feet is very important, because if you enter a pressure, the pressure is going to be set, is going to be attached to the datum. Okay? The calculations are going to be made in the datum. So for us, it's very important to set the datum correctly here. So the tubing has no problem, it's 4800, but the casing, we're going to stop the casing at 5000. Okay? The tubing internal diameter is 2441, and the roundness is going to be 0.0018. The casing internal diameter is 6.1, and the roundness is going to be also 0.0018. This rate multiplier are numerical artificial numbers that multiply the rate many times as the number you enter here. But because we want to get the real rate, we are going we are not going to change this number. It's 1. Okay? We are going to multiply by 1. Okay. Here, if you don't know, if you know some data of your tubing or your casing, but you don't know the internal diameter, that is the data you have to enter here. You got here in equipment. If you click here, you will get a tubing or casing database. If you click any of them, for instance, the casing database, you will get different casings from manufacturers, type, specification, seal, the casing OD, the weight, and the wall thickness, and you can select one of them, copy it, and then you can paste it here. I'm going to cancel that. You can paste it here. Okay. But we know the idea of the casing and the tubing, so we are done here. Then is the turn of the geothermal gradient. The geothermal gradient we have here that at surface we have 60 Fahrenheit degrees, and for the datum of the reservoir we have 180. So 0 and 5000 we have 60 and also 180. And here the software, the model is asking for a overall heat transfer coefficient. The overall heat transfer coefficient, also called the U-value, this is a composite number that captures different heat transfer mechanisms taking place between the well and the fluid. They depend more on the fluid than on the well. Okay. For gas, we have some starting point. Now, for gas, we will use 3 BTU per hour per square feet per Fahrenheit degree. For condensate, we are going to use 5. And for oil, we are going to use 8. Because we are talking here about dry gas, we will use 3. Okay. And with this is done. And last but not least, the average heat capacity. We will always leave this screen as is, no? So these values are theoretical values and they are not going to change. So here we have finished with the equipment data. Clicking down here and we will see that we have some red checks here. If we double click here again and we click on summary, we will get what we entered to the model. And here in draw downhole, we will see that the flow is going to be through the casing from 5000 to 4800 and from 4800 to surface through the tube. Okay? This data is the data that the model is going to use for creating the VLP curve of vertical lift performance, which is the curve of the demand of the well, how much the well can lift, how much gas or how much oil or water the well can lift, and depends on the geometry of the well, if the well is horizontal, slanted, or vertical, and also depend on the diameter and if we have safety valves and the diameter of the casing, the tubing, and so on. No? Okay. Once we finish here, we have to go to the IPR data. Here we are going to enter the reservoir data. So here we are going to select one model. In our case, we will click on Petroleum Expert. Okay, and we will enter the skin by hand. We have the skin because we already had a well testing analysis, and from the well testing analysis we got the value of the skin. Okay. So the petroleum pressure here is 2,500. The reservoir temperature we say is 180. The water gas ratio is 0. We're not going to produce water, and the condensate gas ratio is 5. So we can here we have these orange buttons. We can click here on validate. And clicking on validate, this one turns green because we selected the model already. Now we have to click on input data, and the model is asking for some additional data, like a reservoir permeability. The reservoir permeability is 25 millidarcies. The reservoir thickness is 80 feet. 80 feet. The drainage area is 240 acres. By the way, you can change here to any other unit. Clicking in the unit, you can change to any other unit that you have. And the depth factor, the depth shape factor, what is that? Okay, in 1965, this studied different combination of well location and drainage radius geometry using numerical simulation, and he found a series of factors to correct the semi-steady flow equation. I have here the result of his job, no? And for instance, if your drainage area is circular and the well is in the middle of the circle, your correction factor is 31.6. And this is the one that we are going to use in this course most of the time when talking about vertical wells. But you could have any other shape for your any other shape for your drainage radius. It could be square or an hexagon or triangle or rectangles or whatever. So you will get different factors for different shapes. Okay, you have here a lot of shapes. You can find this at any reservoir engineering book. No? Okay. In this case, because we say we are going to use the circular one with the well in the center, is 31.6. 31.6. If you have information about the geometry, you can click here and you can enter the parameter and you can calculate this factor. Okay. The wellbore radius 0.354 feet. The perforated interval is 60 feet. The well was recently drilled, so we don't have too much days of production. We have 20% of porosity, 30% of initial water saturation, and the software is going to calculate the non-Darcy flow factor. No? The permeability that we enter is total. It could be the gas permeability, but most of the time we are going to enter the totals. Here we can validate. Now we have this tab in green, that's fine. The red one is asking for the skin. We know the skin from the well testing analysis is 5. The well is damaged, 5. We can validate here and we already have everything green. So we can calculate our IPR curve. Once calculated, we can get the curve. This is our IPR curve. This curve means, this curve is this curve is called the offer curve also. It's how much gas, oil, or water the reservoir can offer to the well. No? In this case, the maximum rate that we can get from our reservoir using a single well is 52.8 million. We're not going to produce more than that. Theoretical, no? Because these are values of pressure and these are rates. What happened? This is the reservoir pressure. If we have at the bottom hole the same pressure as the reservoir, we're going to produce 0. But if we reduce the bottom hole pressure, we're going to increase the rate on different, for instance, from 2,000 to 100 to 1,250, we are going to produce something very close to 41 million of standard cubic feet per day of gas. No? So this is the curve of how much fluid the reservoir can offer to a single well. In this case, vertical. No? We can finish here, we are done, and now we have our curve here. So we are ready to make some analysis. The first analysis, the first question that we have to answer is how much is the initial gas rate if the wellhead pressure is 500 psi. We can say, okay, here in calculation system 3 variable, or we can click here in system 3 variable, and the model is going to ask for the top node pressure because we didn't model any surface equipment. The top node is the wellhead, so we can say here, okay, it's 500. The water gas ratio is 0, and we know the condensate gas ratio is 5. Okay, so we can continue. We are not going to make any sensitivity for now, so we can continue here, and here we can calculate. So we got here the results here in this screen For 500 in the wellhead, the solution node is at bottom, is a bottom hole. At the bottom hole, we are getting 2094 psi. And with the 500 in the wellhead, we are producing 19.4 million. Okay? We can see here, if we click plot, system plot, we can see our IPR curve, and with the 500 psi of wellhead, this is our VLP curve, and the intersection between them is the 19.4 million of standard cubic feet of gas that we are producing. Okay, so this is the VLP and this is the IPR. Here we have some E. We have a warning here: erosional velocity limit exceeded. What does this E means? E indicates that the erosional velocity limit has been exceeded. This means that the flow of gas is able to carry sand fines that erode bottom hole and surface equipment. So this means that if we produce this rate, we are going to produce sand, and possibly we are going to erode our equipment. Okay? So that's it. Let's click main. We answer the question. It's 19.4 million of standard cubic feet per day. The next question is, okay, now we would like to get the well performance curve. Okay, the well performance curve is a curve between rate and wellhead pressure. So we have to make some sensitivity. Let's click exactly in the same place. Let's continue here, and here we are going to make a sensitivity. Sensitivity of what? Sensitivity of the wellhead pressure here. We can write down here the values that we would like to get in the sensitivity, but the best thing to do here is to generate. Let's generate, and let's say step to get number without decimal. My first value is going to be 50. I'm going to say, okay, I'm going to start with 50 psi in the wellhead. I would like to have 10 values of pressure. I will increment then maybe in, I don't know, 250 maybe. Let's generate, and we will get this value. Let's change this one for 2,100 maybe, because 2,300 is too high. Okay? And because we know the answer for 500, let's write here 500. Let's continue and calculate. The software has calculated one VLP curve for each value of wellhead. So for 50, we are getting this rate, 19.9. And then increasing the wellhead pressure will decrease the rate. Why? Because increasing the well pressure will increase the bottom hole pressure. So the difference between the reservoir and the bottom hole is going to be less, it's going to be smaller. And smaller the difference, smaller the drawdown or the potential between the reservoir and the well, smaller the rate. Okay? So as you can see, the rate is 17 million, 13 million, then 10 million, 6 million, and eventually we are getting a very low rate with 2,100. Okay? We can see graphically this result in two different ways. First, plotting the system. Here you will get a VLP for each wellhead pressure intersecting the IPR. Okay, this is the rate with 50, and then we will be reducing the rate. Okay, this is one way. The other way, and I think it's better, is clicking here in sensitivity. In sensitivity, we will get a plot like this, but this is pressure in the bottom hole and the pressure in the wellhead. This is not what we want, so here clicking variable and clicking gas rate, done, and here we will get a very interesting curve. This curve is the answer. This is how to say, this is the well performance curve. For 50, we are producing 19.9, and then if we increase the wellhead pressure, the rate will decrease. Okay? Easy peasy. This is the second answer to our thing. Very important here, we are not going to produce 50 psi is very low. It's a very low pressure for the wellhead, so we are not going to produce with this well more than 20 million. This well is not going to produce more than 20 million, although my reservoir can offer, if you remember, 52 million. The reservoir can offer, the reservoir can offer 52 million, almost 53, but we are not going to be able to produce more than 20, okay? The last question is, please export these results to a simulator. For exporting the results, we can click here in VLP 3 variables. And here we can enter the top node pressure, and the water gas ratio we know is 0, and the condensate gas ratio we know is 5, okay? Before we let the software to find an automatic method for the rate, but here we are going to change this. We are going to click user selected, okay? And here for the rate, we are going to say, okay, let's generate the rate here in this button. And for generating the rate, my first value is going to be 0.1 million, very low rate, very low rate. I'm going to get 20 different rates, and I'm going to increment this rate, let's say from 1.1 million. If I click generate, I will get these values of rate, and this value is very close to 20. Because I know the well is not going to produce more than 20, this 21 ensure that I'm including in the export to the simulator the case when the well is in the maximum, and with this 0.1, I mean, here I have a wide range of from the well is closed to the well is producing its maximum, okay? So now we can click and continue, and for exporting to the simulator, we need to export 3 variables. The first one is always the wellhead pressure, okay? In the case of gas, wellhead pressure. The second one is the water gas ratio, and the last one is the condensate gas ratio. We know this gas is very dry, so we are not going to make any combination of value here. We are going to click to write here 5, and that's it. We know the gas is very dry, okay? For the wellhead pressure, we can use the same value that we used before, okay? So here in step, I can start with 50 with 10 numbers, and we can increase this to 50, right? We can generate, and we can say here 2200, and we know that with 2200 we are considered the scenario where the well is closed, okay? And finally here the water gas ratio, because we don't know about the drive mechanism of this reservoir yet, because this is the very first well that we drill in this reservoir. Here we can try to send to the simulator a very wide spectrum of values, okay? So we can say here generate, and in generate I will use step again. I could say, okay, let's say I'm going to start with 0 or no water production, and in 10 values I'm going to increase this in 30 barrels per million, I don't know, to 270 barrels of water per million of standard cubic feet produced. That's a lot. So here we are going to send to the simulator a very wide spectrum of value of water production. No? We have to know more about the dry mechanism of the reservoir. We don't know yet. So let's click continue, and we will calculate one VLP curve per combination of curves, per combination of the values that we entered before. No? This is maybe taking a while. This software is very quick. Yeah, that's it. And here, what we can do is here we can change the first not pressure here, the wellhead pressure, to see what's going on. See? Every VLP, we can also change the water gas ratio. And very interesting here, we are getting another warning with a T, velocity less than Turner criteria. What does this mean? Well, this means that our rates are below the minimum Turner velocity criteria. Above the minimum velocity, Turner velocity criteria, the gas can carry liquids, condensate water, as small droplets in mist flow. Okay? But what happens when we are below? When we are below the Turner velocity criteria, the liquid can condensate in the well, and the condensated liquid reduce the ability of the well of producing gas. So this is very important. We have to be always above the minimum Turner velocity. In this case, these very low rates are allowing the liquid to condensate in the well. Okay? But it's something that we can control. We can control it. So here we can see in plot, we can see every single VLP curve that we have created and to export to the simulator. As we can see, we have many. The quality control here is only see that the shape is the hook shape, and that's it. We cannot do too much quality control here. So let's finish here, and then we will export it to a simulator, clicking here in Export Lift Curve. And here we can select the simulator. For instance, Eclipse or Pegasus or VIP or Roxar or Gap and Ball or any other. For instance, let's send it to Eclipse. Click in Eclipse, continue. And then here you can say a name to the simulator, to the file. Vertical gas well, for instance. Vertical gas well. You click Save, and this is the file that is going to go to Eclipse, and Eclipse can understand this file. And here you have the rates, you have the VFP Pro keyboard. This is beyond this course. We are not going to discuss this, but here you got the gas rate, the THP, tubing head pressure, water gas ratio, and oil gas ratio, and the curve. Okay, the combination of values. Eclipse is going to use this curve for producing the oil from the grid to surface. You can also send it to the Landmark VIP software. You can click continue here. You can give it a name also, gas well, for instance, gas well. Okay, and this is the file that is going to go to VIP, sorry. And again, you have here the keywords of VIP and the combination of values. And that's it. That's it. With this, we have answered the 3 questions, and we have finished this first video. Now we know how to set up a model of a gas well, and we know how to get the initial rate, how to create the well performance curve, and also how to export to a simulator. In the next video, we are going to set up a vertical oil producer well. Okay? It's very similar to this one, but we have to do it because it's the file that we are going to use a lot during the course. So thank you so much for watching the video. I hope the video, I hope this is going to be useful for you. Thank you so much and take care. If you have any question, please don't hesitate to ask me in the comments, or you know my LinkedIn. Please ask me in my LinkedIn. If you make the question public, maybe another person can also be gratified with it. So please try to do it. But by the way, you will get my email at the end of the video. If you want to ask something privately, you can also do it. Okay? Thank you so much and take care. Thank you so much.